Must do the shadow trim. Okay, I am going to, I know, I'm just going to review. I've got to get this last thing in, because once again, for chemistry majors especially, it's an important topic. You certainly know about bonding and anti-bonding orbitals. But what does that mean? I mean, bonding, well, they bond. Anti-bonding, they repel. But why? And I'm curious as to what you know, because this is all I know.
Like, yeah, I asked myself these questions when going through organic chemistry and learning about these orbitals. I mean, that's basically all the theory they go into, is that they're repelling if they're at the higher energy levels.
They're just accepted it.
Just accepted it. As with every other class, hey, look, I left my office open. I'm a genius. Hold on. I'll have Chad keep an eye out if nobody goes and steals something or changes his grade. So that's what we're going to look at today, is to try to understand why we have bonding and anti-bonding orbitals. And then when we're done with that, if there's time left in class, we'll start a review. So, yes, you learned lower energy, higher energy, right. Let's get into it. We're going to start by saying what happens if we have two indistinguishable or distinguishable electrons. So we're going to compare distinguishable and indistinguishable. And of course, our frame of reference to this, because we want to understand bonding, is we'll think about two atoms that are close enough that their electrons are not overlapping. And are they distinguishable or indistinguishable is going to be part of what we're doing. So the first thing, the way it functions for two particles is a superposition state of each possible state. Right? You don't have, if you have two electrons that are together, especially if they're indistinguishable, but it does say indistinguishable, yeah. If you have two electrons that are indistinguishable together, for instance, we bring two hydrogen atoms together, so we've got those two electrons. We can't say this electron belongs to this atom and this electron belongs to this atom. We simply have these two electrons. And so we have their energy states, and so we have here, one is in state A, one is in state B. And the only way, if they're indistinguishable, to write out a wave function for them is just like what we learned when we did the singlet and triplet states. For the m sub s equals 0, we have symmetric or anti-symmetric solution. So we're going to have the same thing exactly here. 1 over square root 2, that's our normalization factor. And then we have psi subscript A for particle 1. So state A is particle 1, state B particle 2, plus or minus, plus for symmetric, minus for anti-symmetric, psi in energy state B, particle 1, psi in energy state A, particle 2. So just to make sure we're real clear, we have A with 1 here, A with 2 there. Right, so it's not repeating the same thing. So here we have a state. Now, two different ways of doing this. And they're fundamentally different because one is symmetric, one is anti-symmetric. So we're going to talk about the exchange operator here in just a second. But that sign, the symmetric versus anti-symmetric, is really important. So we distinguish the particles based on which way they are. If they have the plus sign, that means they're symmetric under exchange. What it means to be symmetric under exchange is if you exchange particle 1 with particle 2, there's no difference. Then we call them bosons because they're explained by the quote statistics, first worked out by Satyendra Bose and then further refined by Albert Einstein. I was reading something yesterday, I think it was yesterday, about Einstein and how many Nobels he really should have won. And the person came to the conclusion he should have won 7. And they talked about his work here with Bose and mentioned that Bose never got a Nobel Prize, and he certainly deserved one as well for his work here. Yeah, they would probably split it. Then if you have the anti-symmetric solution, then you call them fermions because it follows the statistics worked out by Enrico Fermi and Paul Dirac. So a new definition, remember I said fermions are things with a 1/2 integer spin. There is a correlation between that and these definitions. Right? It's not two completely separate. There's a correlation there. And we'll see something leading us toward that in just a minute. So two different ways of combining indistinguishable particles. Now we're also going to compare, I guess I got something before that. I've got two things before this. I don't remember the order of my slides apparently. This is just a reminder of what fermions were, what we said before, the half integer, and electrons, protons, neutrons is what I've talked about. If you want to include quarks, the quarks are also fermions. And there's lots of other particles that are fermions as well. So here it's just re-showing the antisymmetric function for the fermion. And this is the really important statement. Note that the function collapses if both particles are in the same state. What we mean by collapse is if we say, okay, I'm going to have particle 1 in state A and particle 2 also in state A, then I have psi sub AR1, psi sub AR2, minus psi sub AR1, psi sub AR2. That's just 0. And so it is a simple mathematical fact that you cannot have an antisymmetric wave function for two indistinguishable particles in the same state. And if they're fermions, they must have the antisymmetric equation here. And so the end result is you cannot have any two fermions in the exact same state. And so that's what the Pauli exclusion principle is. It applies to all fermions. And so, certainly when I learned it, I thought it applied to electrons, the end. But it's a mathematical outcome that applies to any fermions. With bosons, no such problem. With bosons, if you have psi AR1, psi AR2 plus psi AR1, psi AR2, well, it's just 2 psi AR1, psi AR2. No problem. So bosons, they can be in the same energy state. They don't have to be in a different state. And then we get to the exchange one that I was trying to jump to earlier in my presentation. The exchange operator is saying, okay, the exchange operator is a magical operator that's going to switch particle 1 and particle 2. So it's just saying, I switched the two particles. Now it's pretty clear. If I switch the two particles and I switch them again, I'm back to where I started. So the eigenvalue for p squared, for exchange operator twice, has to be 1. Which means that the eigenvalue for p is square root of 1. What's the square root of 1? Plus or minus 1. Right? In this class, we've learned we really have to pay attention. We do have the 2. And so you have two eigenvalues for the exchange operator, plus 1 or minus 1. And now we can quickly analyze this. Just looking at the boson, if I have the parity operator acting on the boson, then that's going to be switching R1 and R2. What is it like if I switch the R1 and R2? How does this change if I switch R1 and R2?
Then you get 2 psi A R2.
Well, no, if we switch this with this and this with this. So this becomes psi A R2, psi B R1.
Yeah.
And this is psi B R2, psi A R1.
Yeah, it's just the same.
It's just the same. So that's going to have the parity operator acting on this is going to have 1 because it's just the same. What if I did the parity operator on this one? If you switch R1 and R2, you have a plus psi A R2, psi B R1, minus psi B R2, psi A R1. It's opposite sign. So this one has a minus 1 for the parity operator. So we have the different eigenvalues depending on which state we're in. It's an easy way that we can think about differentiating which one. Basically, symmetric is 1 for the parity operator. Antisymmetric is minus 1 for the parity operator. That's redundant. Now, what we're going to do to try to understand this better is, and this is just a single example of how things are different when you compare a fermion to a boson. And it's going to lead us into understanding the bonding and anti-bonding orbitals. So we're going to look at the expectation value of separation squared. Well, I said separation squared. Yeah, that's right. So expectation value of separation squared should be expectation, you first do the square, so you have x1 squared minus x1 x2 minus x2 x1 plus x2 squared. And because x1 and x2 are separate particles, it doesn't matter what order they're in. So that's how we combine those to get this here. So if we take that and we do it for each of 3 different ensembles, first we'll do distinguishable particles. Distinguishable is like this electron belongs to this hydrogen atom, this electron belongs to this hydrogen atom. I can tell them apart. Or, it could be, this is the blue electron, this is the red electron. Something where I can distinguish them. In that case, then my wave function, I don't have to do anything funny. There's no superposition between 2 states because there's only one state. I can tell them apart. And so if I do expectation value of x1 squared, surprisingly enough, I had mistakes in this from last year. I put these, they're completely separable integrals, so I put the x1 stuff here, the x2 stuff here. What is this exactly? Definition of integral psi mod squared dx over all space? 1, right. So that's the definition of normalization. It has to be 1. This one here is the definition of expectation value of x1 squared. And so because it's x1 psi a, it's going to be the expectation value of x squared in state A. So out here it doesn't say x1, it says x squared in state A.
Why is the psi b stuff in there? I don't know.
Okay. So I'll do this out longhand. I have not figured out why I tap it, and sometimes it flashes but stays. There's the standard way of writing the expectation value. This has 2 variables, so that's why I have dx1, dx2. And so then I'm just substituting the wave function psi1 and psi, well, I'm substituting this right here in. And so this is equal to, and I really should have color coded. Let me. Get this so easier for the next step. So there I've expanded out. And now because x1 and x2 are different variables that don't interact with each other, I can move things with x1 past things with x2. This integral here is actually 2 integrals, right? One for x1, or one for x2 and one for x1. And so now I'm just going to move the integrals. So I'm going to have integral for x1 of psi a star x1 squared psi a x1. Oh, forgot the dx1. Then integral over x2. Now when I put the subscript of x1 and x2, I'm just indicating which one it is, the integral sign for, of psi b star x2 there's no operator there. Psi b x2 dx2. Now, x1 and x2 are only important in that they're saying for particle 1 and for particle 2. So at this point, this here has the value of expectation value, come on, go away, of x squared, and then I put a subscript a because that was in state A. And this one here is just 1 by the definition of normalization.
Okay. Why is this squared outside of the...
Because I made a mistake. That's absolutely wrong.
Okay.
Yeah, thank you. I believe I had it right here, but now if we did it with x2, by analogy, since x1 and x2 are just labeling the particles, you're going to get exactly the same thing, but now it was state B because we had particle 2 was in state B. And then if we do expectation value of x1, x2, once again, we can separate the x's. And so we're going to have x1 with the psi A mod squared, x2 with the psi B mod squared. So we just have this here is expectation value of x in state A, and this is expectation value of x in state B. And so we can then write out this expectation value of x1 minus x2 quantity squared by substituting those three calculations is x squared expectation value for state A plus x squared expectation value for state B minus 2 times expectation value A times expectation. Pretty simple, at least compared to what we're doing on the next slide. Honestly, when I was looking at this, I was like, am I seeing double? Are there 2 copies of this on top of each other? It's kind of dense. So now we're the bosons. So the bosons, we have a plus sign here because they're the symmetric solution. And so with the bosons, we're going to have something much more complicated because this, oops, just went too far. This is our psi star, and here's our psi. And to save us all a lot of hassles, I just wrote the answer. You can go through and multiply all of those together, so you're going to get 4 terms, and then go through the math, and you come to this result. So that's x1 squared, and I didn't even do x2 squared because it's going to be the same, except for, yeah, it's going to be the same. And then x1, x2, well, now we have to change. Again, we have, there's the psi star and here's the psi. But we have an x1 and x2 separate. And it comes out to give us this. That's what we had before, plus a new thing. And so that new thing is going to make it different. So if I then take the expectation value for the separation squared, I thought you had a question. I have, okay, this is the definition. This here, actually, I think had the -2, right? Yep. This here is what we had for distinguishable. But then we have minus this additional term. Now, when we do a mod squared of the integral, mod squared is always going to be positive. So that means that this additional term, what's it going to do to the separation, the expectation value for the separation? Is it going to increase it, decrease it, or make it stay the same?
Increase it? Oh, it's positive inside.
Yeah, it's positive inside the mod square. So what's it going to do? Decrease it. So as an outcome, we can see right now, bosons are closer than distinguishable. So that's something interesting. Bosons can get closer than distinguishable particles can. In fact, there's a force to push them to do that we call this exchange force. Now, if we do it with fermions, we change that plus sign to a minus sign. The work is all the same, but the outcome is this sign got flipped, which makes this here is again the distinguishable, but then it's plus something. So what happens with the fermions? They get pushed apart. So we have a fundamental outcome now that distinguishable particles will have some separation. Bosons will be closer, fermions will be farther apart. Which suggests then, well, maybe fermions aren't going to share much space compared to bosons. So important outcomes. When the particles are far enough apart that the wave function of one is 0, where the other particle's wave function is non-zero, then we consider them distinguishable. So to take as an example, in theory, a hydrogen atom here in this room, its electron has a certain probability of being on the moon. How big is that certain probability? Vanishingly small. So we would say, yeah, its wave function is approximately 0 there, so it's distinguishable from any electron on the moon. Furthermore, if I have two hydrogen atoms that are separated by a millimeter, the probability of an electron from one hydrogen atom being at the position of the other is essentially 0, right? Going to the moon was an extreme example. You don't have to. Second, these exchange forces pull bosons together but push fermions apart. So how is this going to play into what I promised at the outset, talking about bonding and antibonding orbitals? Well, for starters, we have to include spin. So we talked about spin. If we're talking about two particles, the two particles could be in a singlet state or a triplet state. What was the difference in the singlet state and the triplet state?
The triplets, they had different spins.
Okay, the triplet state, we had a spin of 1, and it was symmetrical. That's the key we're looking for here. The triplet state was symmetrical, and the singlet state was anti-symmetrical. And if electrons didn't have spin, you notice this statement, you'd have no bonding if electrons didn't have spin. If they didn't have spin, the fact that they're fermions means that they would always be pushed apart and repelling. You would never have electrons pulled together. So how is it that we can have, I said fermions gave me that pushing apart wave function, right? Well, it gets a little more interesting than that. The spatial wave function multiplied by the spin state must be antisymmetric. Before we just said, I thought I had the highlighter. Before we just said that the spatial function had to be antisymmetric. It turns out that was an overstatement or an understatement. What's true is that the complete wave function must be antisymmetric. So if you have a symmetric spin state, you must have an antisymmetric spatial state. If you have a symmetric spatial state, you must have an antisymmetric spin state. So what that means is if I have a singlet state, you told me that is antisymmetric. Then I must have, actually, so this is spin state. And so the spatial state, must be symmetric. So when I take the product of, think of antisymmetric -1, symmetric 1. I have to have the product of those two as antisymmetric -1. So if I had antisymmetric, I'd have -1 times -1, it'd be symmetric. Or symmetric times symmetric, 1 times 1, it'd be symmetric. So I have to have if it's anti-symmetric, which is what the singlet state is for spin, then the spatial must be symmetric. But the spatial symmetric, yes, is the one that was attractive. So two electrons in the singlet state are going to have a symmetric spatial function, and thus they'll be attractive and they'll form a bonding orbital.
I'm kind of confused by how you say, like, that the electrons would still be fermions even if they didn't have spin. Because isn't the definition of a fermion that it's a half integer spin?
Yes.
So if it didn't have spin, how would it be a fermion?
And well, they wouldn't be. You're right. Yes, we're playing with some definitions here, and we're saying if they were fermions and didn't have spin, and that's a dumb statement. So triplet state, its spin state is symmetric. And so its spatial state has to be anti-symmetric, which is antibonding, because it's pushing them apart. So when you look at those orbitals, and I'll go back to the first picture here. Chad had said energy, I think, when he was talking about it. Or one of you said energy. This one here is S equals 0. And this one here is S equals 1. And so it's a higher energy state in the S equals 1, and it's anti-bonding because of the then anti-symmetric spatial wave function.
So why do they both have to have anti-symmetric overall?
If they were both anti-symmetric, then you would have had an overall symmetric. I think that may not be exactly what you meant to ask.
I know that the reasoning for why we had to multiply the spin portion for the singlet state by a symmetric spatial portion was so that we would end up with an anti-symmetric overall.
Yeah, and in fact, if I was really careful here, this here is things that have an overall symmetric wave function and things that have an overall anti-symmetric wave function. If it's a boson, it has to have an overall symmetric. If it's a fermion, it has to have an overall anti-symmetric.
Okay, so as long as it's already fermion.
That would be the correct way of doing this. So the fermions are the particles with 1/2 integer spins. The bosons are ones with integer spins. And so if it has half integer spin, you have to have an overall anti-symmetric wave function.
So last Wednesday when we were doing the singlet and triplet state,
Yes.
were we talking about indistinguishable or distinguishable spin?
We were talking about indistinguishable.
Because that's what you were talking about, but your slide said distinguishable, so I didn't know.
Whoops. Yeah, I was talking about indistinguishable. Okay, so this is where we, I think, left off. So, oh no, I did that. Now we're past where we left off. Okay, so this is then summarizing what I just said. A singlet state is anti-symmetric, so must be joined by a symmetric spatial wave function if it's a fermion, and symmetric spatial function will bond. Whereas the triplet state is symmetric, so it needs the anti-symmetric spatial function and cannot bond. So, what are we showing? We're showing mathematical rules that it turns out are correct. So you learned, like in chemistry class, you just learned these are rules. And now you can see, okay, there is a solid basis for where it comes from, even if it's kind of confusing. Unless you find it not confusing. Then you're doing better than me. Some other outcomes besides bonding and antibonding states. White dwarfs and neutron stars. So, do you guys know what a white dwarf is? Okay, I got a yes and a no. White dwarfs are the remains of dead stars that were less than, let's say, 3 solar masses when they died. We talked about in general physics class today the nuclear fusion and what's going on in a star. And so our sun is going to end up with carbon. And then after it's all done, everything will just shrink down. But something stops it from shrinking down to a point. And that's what we call electron degeneracy. Now, we haven't really talked about degeneracy in this class like we probably should have. Degeneracy is a term that means that you have more than one energy state with the, or more than one state with the same energy. That's what degeneracy means in quantum physics. But when we talk about electron degeneracy here, what we're talking about is the fact that no two indistinguishable fermions, and we're focusing on electrons for this. We focus on electrons because they have longer de Broglie wavelengths. No two indistinguishable fermions can have the same exact state. Otherwise, your wave function collapses. So that means that as you pack more and more pressure on that white dwarf, the carbon atoms, well, something I probably should have said to begin with. In stars, because it's so high energy, the nuclei are completely ionized. So I say a carbon atom. What I mean is 6 protons and 6 neutrons. There's no electrons involved. But it is electrically stable or neutral. So you have a bunch of electrons, they're just not bound to any nucleus. And so you basically have electrons and nuclei that are hanging out together. And the nuclei would collapse more, but the electrons won't let them because the electrons are being held up by the fact that they can't share the same space if they have the same wave function. And so the more you try to compress it, the more you have to raise electrons up to higher and higher energy levels so that they can spread out their energy levels. So it takes incredible energy to compact it. If you put more mass on, of course, you do have more energy, and it does compact very, 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 very slowly. So you add mass, and it very, very slowly will shrink on you as you add mass. Until you get to the point where you force something to break. Basically, I've been thinking about this. I think it's if you force it so all the electrons are really in different energy levels, well, then it can collapse, right? Once they're in different energy levels, it can collapse. And at that point, then you have something catastrophic that occurs. We call it a type 2 supernova. Type 2? I think it's a type 2, yeah. A type 2 supernova where you have the entire thing then goes kablooey and blows up. So 1.4 solar masses is the maximum mass you can put on it before you have enough pressure to force to overcome that degeneracy and to force it to go kablooey. So you can actually do some calculations on it. The degenerate pressure, and I think the textbook has this carefully laid out. We clearly, since this is going to be our last lecture with anything new, I promise, we're not going to be able to go through the background of this. But NE, that's the number of electrons per unit volume. So this here is a term that means the electron density. So the degenerate pressure, the pressure that you have to have in your electron gas, as we call it, is proportional to the electron density raised to the 5/3 power. That as you put more mass on, you're going to increase the pressure, and you're going to then change that electron density, and it'll slowly increase as you put more mass on.
So you're saying by collapse, you're talking about like making them basically be forced into carbon atoms instead of this cloud of nuclei?
It's actually I don't want to overstate things here, so I'm going to decline to answer because I'm not going to be perfectly right. It's forcing everything closer together, and the nuclei actually are okay. The carbon nuclei, they're not compressed beyond anything that they can't handle. It's the electrons that's keeping the whole thing from being further compressed. And then you force the electrons in, you force them actually into the nuclei, and you have then interactions between the nuclei and the electrons that makes everything go kablooey, is my understanding.
Release of energy.
Huge release.
Okay.
Okay, so yeah, the reason that we're doing electrons here is because they have neutrons can pack more tightly. Yeah, neutrons have the shorter de Broglie. Yeah, I was right. De Broglie wavelength is longer for the electrons, and hence those are the ones that keep it from collapsing. The protons and neutrons would have much shorter wavelengths. They would be important if the electrons weren't there. So that takes us to the next step. If a star dies with a mass more than 1.4 solar masses, it dies differently. It dies differently. The electrons are forced into the nuclei while it's dying, and it actually converts, it's not a direct process, but it converts the protons into neutrons. And so if you have a mass more than 1.4 solar masses when it dies, it will basically convert all of the nuclei, carbon and oxygen generally, into neutrons. And then the neutrons essentially form a nucleus. It's just like the nucleus of an atom, except for it's billions and billions and billions of neutrons with maybe the occasional proton or something that didn't quite make it through the process. So that's called a neutron star then. And what keeps the neutrons from collapsing? Well, neutrons, are they fermions? Yes, so the Pauli exclusion principle applies to them. Now, because you don't have this electron gas anymore, they collapse much more, like 1,000 times smaller. And it's then the neutron degeneracy that keeps it from collapsing. So you have an equation just like this one here for the degenerate pressure, except for it's going to be mass of a neutron and the neutron density there. And so this can handle at least 2 solar masses, maybe up to 3 solar masses for the pressure that will be created. And when you get up above that mass, nobody knows what's going to happen. It all is going to be crushed again, and it's going to be crushed into a volume that's smaller than what we call the Schwarzschild radius. That is, the Schwarzschild radius is the farthest distance away from the center of mass where light can escape. If you're closer than that Schwarzschild radius, initially it was just Newton's universal law of gravitation says that no light can escape. With Einstein's relativity ideas, you have the space folds in on itself and nothing can escape. But in both cases, you have a black hole. And so if you put more than about 3 solar masses there, it just crushes to a black hole. What's inside a black hole? Your conjecture is as good as anyone else's. I mean, they know a little more than you probably, but nobody really knows. So I have a couple ideas here. One idea is a quark star. That is, maybe the neutrons are going to break down into the quarks because the neutrons and up, down, down, right? 1 up quark, 2 down quarks. Maybe we're going to have something that is a quark star where it's quark degeneracy that holds it up. But we'll never know because that's inside a black hole. We can't probe inside a black hole.
Never?
Never. You go inside the black hole, sure you can, but you can't tell me. And of course you won't live, but that's beside the point. So we really don't know what's going on inside a black hole. And there's good theories about it, but they're not, shall we say, supported theories. They're just theories that we wish we could know more on.
So the first mass that you're talking about was the mass of the star when it dies.
Yes.
And then the second type of mass is the pressure you're using.
Well, it's the same mass.
Yeah.
It's the same mass. I'm now done with all new material, so now we're ready to review. But when you talk about a star, you take a star like our sun. our sun has a mass of 2 times 10 to the 30th kilograms. And it's losing literally tons of mass every second. I think it's millions of tons every second. But compared to its overall mass, it's negligible. But when it gets to its death stage, our sun, what we're talking about in class today, when it gets to a death stage, it's going to run low on hydrogen in the core. The core will compress. It'll start fusing helium. And what I didn't say in class, you'll have a shell of hydrogen fusion that goes out through the star. And that shell goes out really quickly. And when the shell is burning outward and the core is collapsing, it turns out that the whole star expands. And as it does this, it starts throwing off way more mass per second. And so stars lose a lot of mass in their death stages. And if it's a really big star, like let's say it's a star that started with 10 solar masses, so 10 times the mass of our sun, as it's going through its death stages, it'll probably throw off more than half of that. And so its final mass is smaller, but that final mass is the mass we're talking about in every case.
And then by the pressure, how are you putting more mass back on it?
So how are you putting more mass back on is a tricky question. That only happens if you're in a binary system. If you're in a binary system, you have this star here that's already died. So it's a white dwarf or a neutron star. Then you have this one, as it dies, it's giving off mass. This one here's got a lot of gravity. It collects a lot of it. That's how they can gain mass. Okay, so now it's time for review. So everything from here on, we're going to review in kind of backward order, review the hydrogen atom, and then go back to the previous chapters. So what are these pictures of? And these are experimental pictures of electron density. I think it was for hydrogen atom. So that they can actually image the electron densities and see that they do. This is, I believe, a 1s. Oh, blue on blue. That's the perfect color combination. I think this is 1s, 2s, and I think that's what these are. I grabbed these last year and didn't look them up to verify that that's what they are. But they're actual pictures imaging the electron densities. So reviewing what we did with the hydrogen atom, we started with we had to have a 3-dimensional Schrodinger equation. And so we have the 3D version introduces the Laplacian operator. That's this thing, actually. This thing. That's the Laplacian. And then we went through the separation of variables. We used spherical coordinates because we had sphere symmetry. We have a spherically symmetric potential energy function. We're going to end up with the spherical harmonics, which I don't have shown on this slide.
And we knew it was spherically symmetric because the potential depended only on R.
Yes, that's correct. So we first separated the Schrodinger equation into the radial part and the angular parts because we had 2 angles in our spherical coordinates. And then we took the angular parts and separated those into the azimuthal and the altitude part. And each one of those separations introduced a quantum number. And so we had n that came from separating the radial and, well, actually, no. We had L here, and then we had M that came from separating the azimuthal, and then it was from solving, actually, the radial equation that we got N. So that's where we introduced them. And when we put them in, as you recall, I said for reasons that will make sense later. You know, we put in, well, this is equal to L times L plus 1. Like that made any sense. But in the end, it turned out that that was a convenient way of writing the... I've actually done the work once, just using a random constant and then getting to the end and saying, okay, then this random constant has to equal. But it's just a lot easier to do the math if you put L times L plus 1 right at the beginning. Okay, I just spoke about pretty much all of this. The radial solution, okay, for the angular solution, remember we had to use those Legendre polynomials, associated Legendre polynomials. Yeah, the Legendre function and associated Legendre polynomials. The azimuth one, that was the easy one. That was the one that we could directly do. We didn't have to rely on somebody else because we just had d capital phi, d phi equaled plus or minus m. And so it was quick and easy, or plus minus m phi. The others, we had to do sophisticated stuff, which we didn't do. We relied on others. Likewise, for the radial function, we first found the limit for large radius, then we found the limit for small radius, then we used a Taylor series of infinite polynomial for the in-between. We found a relationship between the coefficients of those polynomials, and then we put in a rule that said this series has to terminate or else we won't have a normalizable function. And putting in that termination is where n came in. And so that gives us our 4, I saw the AKA and I was thinking that was a misspelling. We have the 4 quantum numbers that we need to describe our hydrogen atom. And now at this point, did you know these 4 quantum numbers before you took the class? Okay. What did you know about them and what do you know different now?
Well, I didn't really understand the M sub L and M sub S. I knew N and L, the relationship between, just a very basic one.
Mhm.
I guess I just understand more in depth.
Yeah, I understand more of the mathematical principles behind it, and that M sub S is actually changing, and I think M sub L too are changing the energy from just what N would give.
Yes, and that's an important outcome, right? If it wasn't for that, we would have a different looking periodic table. And so that's a very important outcome, and it's something that, especially in like a freshman physics or a freshman chemistry class is never talked about, right? It's just N tells you the energy. But it turns out it's not so simple. And so that's why, your extra credit paper goes into, here is how these other variables are going to play in. And why do the other variables, why do the L's and M sub L's and M sub S's play into the energies? Because of what force? Yeah, because the magnetic forces. Even if you're not in an external magnetic field, you have the magnetic moment of the orbital and the magnetic moment of the electron and the magnetic moment of the nucleus that are all interacting. And so even if there's no external magnetic field, those still make a difference for the energy state. And then an external magnetic field, well, they're very significant.
And is it real angular momentum that magnetic moment of the particle causes, or do we just call it angular momentum?
The L and M sub L, those are real angular momentum.
Okay.
The others are acting like it. At least that's my understanding. It's my best understanding. Okay, so the spin, very important. Spin, it's a misnomer. It's not a correct term. I say it's very important. You could probably get your whole life in chemistry class or chemistry professional and really not worry about it being a misnomer. But to me, as a physicist, it's important to know, electrons aren't just sitting there spinning. They're not tops, which is what the idea of Gauss-Schmidt and Uhlenbeck had when they coined the phrase spin. They thought of them as tops. But that's not it. It's an additional angular momentum due to intrinsics.
And what's the best experimental or theoretical reason why they're not top spinning? Is it because if we actually calculated how much mass they would have to have?
Well, it's not mass. I've actually had students do this calculation for a homework assignment in the past, but I didn't have you do it. You can calculate the gyromagnetic ratio of a physically spinning object based on its radius. And experimentally, we can confine the radius is no bigger than this. And so you calculate the maximum gyromagnetic ratio you can get, and it's much less than the amount that you would have to have, right? You would have to be spinning such that you were going faster than the speed of light at the radius of the electron, because they're so small. So with our rule that nothing can exceed the speed of light, you are left with it can't be spinning. Okay, and then we just have, electrons. Oftentimes we don't even talk about the total spin of an electron because it's always the same. Right? The total spin of the electron is always h bar times square root of 3/4. What we do talk about is the component that is in the z direction. And what is the z direction?
The one, external magnetic.
Yeah. When we apply an external magnetic field, then we can say, aha, that's the z direction. Before that, it's completely undefined. It's just a random direction in the atom. And you have the bizarreness of what I just said that says that you cannot have the electron's magnetic moment lined up with whatever direction you're measuring. It's never possible. You tend to think, well, okay, so I tried measuring like this and it wasn't like this, so I'll try like this. It's still not going to work. It's just a physical impossibility. I'm out of time, so we'll continue with our review there.
Would you expect us to derive those, separate them into the spherical versus the radial?
Oh, no, I would not.
So just a discussion of how that's done.
That is correct. And there is no homework due this week. I don't know if there's one shown or not, but